In this lesson, we're going to address the question, why should we overlearn information? And the answer will be, making retrieval automatic frees up mental resources in our working memory so we can be better thinkers. Did you ever question the value of drilling your times tables and ask yourself, why should I memorize my times tables? 5 times 4, 6 times 9. Why go to the trouble of memorizing that information? And did you ever question the value of reading on a daily basis? You might say to yourself, well, I already know how to read. Why should I read more frequently? Well, psychologists have an answer. Knowing your times tables and reading a lot makes strong memories in your brain, which helps your brain avoid having to think. See, because we have limited working memory resources, and if we don't have to spend those resources doing the mathematical calculation or struggling with our reading, then the working memory can be used for thinking about other stuff, like the meaning of what we're reading or the next step in a calculation. Now we're going to begin this lesson with reading. So first let's map out some of the language areas in the brain. Here we're looking at the cerebral cortex, and we've got the frontal cortex here, and then we've got the temporal cortex, occipital cortex, and parietal cortex here. We've got two notable language areas, the speech area in the frontal cortex and a sort of language comprehension region at the kind of the border of all three of those cortices in the back. Now these areas sometimes are called Broca's area in the front and Wernicke's area in the back, named after two doctors who had patients with damage to these areas, and they had corresponding deficits in language. So a simplified way of understanding these two regions is that this frontal cortex region is where the brain is sort of planning to say words. And then the back language area is more related to accessing word meaning. Notice that Broca's area is very close to the motor area of the brain. These are the brain cells that are going to be activating your vocal apparatus to make you talk. Now let's consider, what does it mean to possess a concept? The example will be a tiger. Well, neuroscientists think that what we do in our brain is that we store memory traces of the different sensory aspects of a tiger. So, for example, what a tiger looks like would be stored as a memory trace in the visual areas of the brain. What a tiger feels like would be stored as a memory trace in the touch area of the brain, and likewise what a tiger sounds like would be stored as a memory trace in the hearing part of the brain, or near the hearing part of the brain. Now the brain also has other regions of cortex, sometimes called association cortex, that can link together these separated memory traces. What a tiger looks like, what it feels like, and what it sounds like. So this is the area then that is going to be integrating these different sensory aspects of a tiger. We're starting to build a concept of a tiger. And we want to have a concept of the tiger. We want to be linking together all the information about the tiger. So we're just going to put the word tiger here, but that represents sort of a hub of information. It's this area of the brain cells here that are linking together these separated memory traces. And in fact, we might know other things about the tiger. What does it eat? Where does it live? Etc. Those would be stored as, sentences in our brain, and we're going to connect that up to this tiger hub, the concept of a tiger. In addition, we've learned the word tiger. What does it sound like? We have a memory trace for the word tiger as well, and that has to be linked up. So this whole set of integrated information, we would say, is the concept of a tiger. Now, this brain could be the brain of a literate person, one who can read, or a non-literate person, because both literate and non-literate people use vocal language, right? So they have words that they say to refer to things. It's just that literate folks can also read. So now let's consider reading. In a literate brain, when we read the word tiger, our brain must be able to activate the concept of tiger. Let's see what this looks like. Notice down here in the visual area, we're identifying an area called the word form area. It is here where scientists think people store the memory traces for what words look like on paper. Notice it's close to the language comprehension region, and remember we were identifying this as sort of association cortex that is linking up all the different information about tigers. Now the word form area is a brain region activated by strings of letters that make words. Because language colonized the left hemisphere in most people, the word form area ended up in the same hemisphere when reading is learned. The temporal visual cortex is close to the temporal language areas, so only a short circuit was needed to connect them as we were learning to read. And interestingly, the word form area is located in the right hemisphere in the rare subjects who process spoken language on the right side. So now we're going to add another element for the literate brain. We're going to be creating memory traces for strings of letters, for what words look like, and then we're going to be linking those memories up to the concept of a tiger. So this is what's different in the literate brain. Non-literate individuals do not have sets of memory traces for strings of letters. The literate brain does. So reading requires the visual cortex to recognize strings of letters as words that have meaning. In the brain, the letter string has to be linked to the concept associated with the word, and this association involves neuroplasticity as we learn to read the word tiger. So as young learners, as we're learning to read the word tiger, we likely have a book that also has pictures of tigers doing different things. See, so we're going to be connecting what the word tiger looks like with all the information about tigers that we've also learned. And this allows us on a future occasion when we read the word tiger, we will be activating the meaning of the word tiger. All right, we're finally now ready to answer the question, well, why is it important to read on a daily basis? And it's going to have something to do with these memory traces of the words. We want to make them very strong memory traces so that we automatically activate them so as to activate the meanings of the words. Now, to set the stage for this part of the lesson, let's remind ourselves about working memory. We saw this diagram in previous lessons. We have information coming in and enters working memory, and then hopefully we'll store that information in the long-term memory system so that we can retrieve it at a later time. The working memory system is sort of what we're conscious of, what we're thinking about, the information we're working on at any given moment. And in past lessons, we sort of put this box in the frontal cortex to represent the working memory system. There are neural circuits in the frontal cortex that turn on when we have to use our working memory, whereas the rest of the cerebral cortex, we sort of associated that with the long-term memory system. And so when we're having a conscious experience of what we're seeing and hearing and so on, it's the sensory areas in the back of the brain that are sending information to the working memory system. And when it gets loaded up into the working memory system, we have a conscious mental experience of that event. Now here we just need to add the fact that there are regions of the parietal cortex that also seem to become activated during working memory tasks. So it's a bit more complicated than just a frontal cortex region. There is a posterior region as well, and this region is the one we'll focus on for the remainder of this lesson. So now let's take a look at what's going on in the brain of a young child, a novice reader. Let's identify three important areas. We've got the frontal cortex working memory system here. We've got the visual word form area and the visual areas of the brain. And then we've got this parietal cortex working memory region here, what we're calling executive control and spatial attention. Now, in young readers, this area for the working memory shows high activation. It's a difficult task to learn to read. Let's say the example is the word snow. So here the visual area is processing, what these letters look like and feeding that information into the working memory system, and the child is trying to pronounce this word. So they're going to sort of articulate the sounds of these letters. Snow. That's a serial processing task. Not surprisingly, the time it takes to pronounce a word is related to word length. So for the word octopus, well, there's more letters and more syllables. It's going to take longer for the child to sound out that word. Let's remind ourselves that for the novice reader, this is an effortful and slow process. reading activates the working memory systems to a high degree. Now, why is it important that longer words take longer to pronounce? And here's the reason why that's important. Because the child will not be able to access the meaning of the word until they have sounded it out and they have recognized what that word is. So accessing meaning must wait for the word to be decoded. So for young learners, longer words take longer to figure out what they are, and so it takes longer to access the meaning of the word. Now let's take a look at what happens in the brain of a skilled reader. Notice we've got our three areas: working memory, word form area, and the working memory system. Notice we're indicating for skilled readers we have low activation of the working memory system. For skilled readers, there's just lower activation of the working memory system. Now, why would that be? And the answer is down here in the word form area. For skilled readers, they have seen the word snow and octopus many, many times. They have developed strong memory traces for these words. No longer do they have to sound out the words, which takes time to go through the sequence of sounding out the words. They can visually recognize these words and so quickly activate the meaning. And interestingly then, there's no longer a time difference in activating the meaning of the words, because again, they don't have to sound out the longer word to get at the meaning. They just quickly recognize the visual form of that word, just like they would recognize the visual form of the shorter word. So skilled readers, because they have strong memory traces of what words look like, can activate word meanings more quickly. And the time it takes to activate the meaning is no longer related to the length of the word. So this is why we want to read a lot, as much as we can, because skilled readers quickly recognize words and activate meaning. Skilled readers have developed strong memory traces for what words look like, so they no longer have to sort of sound out the words. Automatic memory retrieval frees up working memory to process meaning. Again, remember, for the young learners, they were using lots of working memory resources just to kind of sound out the word, and they had to do all that work before even activating the meaning. Skilled readers don't. They quickly recognize words and quickly activate meanings. Now let's consider mathematics. Here we have the brain of a young child, a novice mathematician. And we're going to give them the problem 6 plus 3. Now, when you measure the brains of these novice mathematicians, you find high activation of the working memory system, in this case the parietal part of the working memory system. And this also, we said, was related to attention. And so scientists think that actually what children are doing is they're shifting their attention along a number line to solve this problem. So here we'll see it over here in the working memory system. Here we got a number line. And psychologists think the child starts at 6 and then counts along the number line 3 units. And then, oh, that's 9. Right, so they get a 6, 7, 8, 9. Now that again is a serial process. It takes time to add 1 and do it 3 times to get to your result, 9. And again, not surprisingly, if you ask them what's 6 plus 7, well, if indeed this is a serial process, it should take longer for them to figure that out. And indeed it does. So again, you start at 6. Now you have to count 7 units up the number line and then read off the result 13. It takes even longer to do that. Right? So again, the processing time is related to how many units you have to move along the number line. And now let's take a look at the brain of a skilled mathematician. Notice we don't have a number line anymore. And also notice we have low activation in the parietal working memory system here. What scientists think is happening is that skilled mathematicians have memorized these values. In other words, they have stored memory traces of the result of 6 plus 3. They don't have to work along a number line to get that result, and likewise for 6 plus 7. They have done those calculations so many times that they have stored the result as a memory trace that can be quickly accessed. So fast automatic retrieval. They don't have to move along a number line 1 unit at a time. And that also explains why it takes the same amount of time for a skilled mathematician to solve these two problems. You see, in the young learner, the amount of time it takes is related to how many counting moves you have to make along the number line. So if I have to move 7 units along the number line, that's going to take me more time than just moving 3. But in the skilled mathematician, there's equally fast access to the result because these results are stored as memory traces. And so they don't have to take the time and the working memory resources to move along a number line. So notice how that's similar to the skilled reader. The skilled mathematician, because they've done a lot of work, they've memorized lots of these calculations, they have quick access to the results of some of these simple calculations. Just as in the skilled reader, they've read a lot of words, they have strong memory traces for what words look like, so they have fast access to the meanings of words. In the case of the mathematician, the skilled mathematician no longer has to take the time to move along a number line. The skilled reader no longer has to take the time to sequentially sound out the word to get at the meaning. In summary then, reading and calculation is easier and faster and more successful if we can rely on fast access to information in long-term memory. And this is why teachers recommend doing lots of calculations with numbers and lots of reading. We want to install knowledge into the long-term memory system. We want to have, lots of words in the word form area, and we want to have lots of numerical calculations stored in our brain. And why do we want to do that? So that we're not taking up working memory resources just to do the basic work of, sounding out the word or moving along a number line. So it does take work to install this knowledge. We've got to do lots of calculations when we're young, and we've got to do lots of reading. But if we can do that, then we're going to be better thinkers because we're going to have more working memory resources to do that thinking.